Thank you, Jamie. Thank you for having me. It's a pleasure to come up here. It's a long story. I mean, I've been in this center since I moved to the U.S. back in '94. So it's nice to come here as a faculty member. I'm in Weslaco now. I'm an agricultural economist, and we got this. What I'm going to present is part of the work that we're doing with the Chevron on biofuel production. Jamie said that we're going to hold questions till the end, so please, I would like to get your views, your input, your comments on what I'm going to present. But please, let's wait until the end. I want to acknowledge my associate here, Juan Monge. He's a research scientist that again was hired through this grant that we got through Chevron. Oops. Okay. First, you're using energy cane as our main feedstock for biomass production. Why energy cane? Well, you got sugar cane in the valley. It's the only place in Texas that we produce sugar cane commercially. Average yields for sugar cane is about 10 dry tons per acre. The energy cane that we're getting right now, and you have some here in the Corpus Center, it's about 19. Actually, Corpus got a little bit over 20, but average about 19 dry tons per acre, which is key to make this biofuel production profitable, or at least close to being profitable. The higher increase your chances of success. Potential low input requirement. We're still working on water. We got a grant to work on using less water for our crops. Wide geographic adaptability. Again, doesn't compete directly with feed or fiber crops. And compared to sugar canes, have lower concentration of soluble sugar, which is desirable. You want high lignin, less sugar. The less sugar, the best. And then you got longer harvest window than other crops like switchgrass or the corn stover or energy sorghum. You can go. You can start harvesting in October and go all the way April, possibly go all the way to May. In the valley, they start harvesting around the end of October and go to the end of March, starting April, depending on the year that they have on the rains. We developed, and my co-worker Juan Monge developed what is called the BIOSIM, which is biomass simulator. And what we do basically, we get information from the production parameters, fertilizer, everything that the agronomists, physiologists give us. We use all the information, not only average. We use all the forced replication, several years that we have already, and we add the weather and yield risk. We also have price risk given the information that we have from FAPRI and from the energy AEA. It's the energy something. It's federal basically. They get projections on prices for fuel. Then we got our production function. Then we have our field plan parameters, which is acreage, harvesting plan, transportation, contractual agreement with producer, which is very important as well if we want to convince producers to plant this material. We got the plant parameters, and this is basically from the literature. Since we don't have a plan, there's no a commercial plant yet. There's a lot of literature on biomass biofuel production, different conversion processes, and we got a location, size of the plant, financing and conversion processes. We have the risk of the biofuel and byproduct prices. Most of this feedstock has a primary product, which is the biofuel, but also has a byproduct that is, I believe in this one is generally electricity produced. In the case when we do napier grasses, we just got a grant also with Dr. Foster here to work on napier grasses and add it as another portfolio of crops. We're going to have dual purposes, either as a forage or as a feedstock for biofuel. So I think it's going to be very interesting as well. We put all that into our financial statements. income statement, cash flow, balance sheet, and then we got our key output variables. We get our KOVs, key output variables, and we present on the profits, capital, and operating costs, life cycle analysis, water usage, and we do our one that we use a lot is probability of success, which is basically a probability of 95% probability of a positive net present value. Usually, net present value, a positive net present value, that means it's a good investment. But because we're using risk, that's why we have probabilities, and we're using as the probability of success, or it will be the probability of 95% chance of success. A little bit on feedstock production. We're using two feedstock, and basically another key for this to work is year-round production, year-round harvesting, sending to the plant. We use energy cane from October to April. Again, depending on the varieties, we will try to stretch it all the way to May. Since the good thing about energy cane as well, or a little bit different about sugar cane, for sugar cane you need to wait until the plant matures to have all the sugars converted as matching to sucrose, all the glucose and fructose. Well, for ethanol production or biofuel production, they don't have to convert to sucrose. You can use all the sugars to produce the biofuel. So we can harvest green cane and also extend it as much as we can. And then the other product we use sweet sorghum in this specific study, but it could be energy sorghum, and hopefully we can get Napier grasses. We can get the information from these other grants, so we can see which one works best in different areas in Texas and eventually in the U.S. We got production costs from Weslaco, Corpus Christi, and Bowman. We have field trials in Weslaco in those three areas, and we got their cost of production from those three areas. And the sweet sorghum is from a study, a thesis actually from our department on sweet sorghum production for biofuel. On the growers' return over production, it depends on the region, but we use 20%, and we also did some sensitivity analysis just to see what happens if instead of 20%, it will take 30 or 40% over the production cost to convince producers to produce our feedstock. And the harvest and hauling costs, we got it from the sugar mill in the valley. So it's actual harvesting and hauling costs from the mill that we have in the valley. Eventually, we want to use a formula that is going to incorporate percentage of agricultural land when we move away from, when we make it more complex our model, because we're going to be we're working, and I'm going to talk a little bit about our future work, but we would like to have a formula that incorporates the percentage of agricultural land in a specific area, the distance, the roadway, so we can calculate the harvesting and hauling costs for specific areas, different regions in Texas and eventually again the U.S. There's a lot of literature on that as well, but for simplicity, in this case, we just use the numbers from the valley. Very interesting, we have data from 2012 and 2013 for Weslaco, and as you can see, it's a big jump from one year to the next. Couple of things, genetics and also management, different ways, and again, here in Corpus, you have seen about the same thing, the same jump. Actually, Corpus goes all the way here to 20. So from one year to the next, this is a big jump, about 2, almost 3 dry tons per acre. You see that the risk is about the same because the plots up, they have about the same risk. And then the sweet sorghum, since we don't have data, we have data from energy cane, but we don't have data from sweet sorghum for a specific project. We use a GRKS distribution using some other work that Juan NCISO and John G. Font has done in the valley. But you use a GRKS distribution that uses a minimum, middle, and maximum. It's kind of like the triangular distribution, but it's a little better because it accounts for the minimum and the value. And the minimum and the maximum value, there's a 2.5% chance of having more and less than that minimum and maximum. For the energy cane, we have data. We did empirical distribution for that, so we have 2 years of data on that, or 8 observations for each variety. Let's go on the parameters for our feedstock. As you can see here, the expected yield, everything is in short, dried short tons per acre. For our 3 areas, we got Weslaco and all of them energy cane. We got 19, 20 for Corpus Christi and 14 for Beaumont. Main reason, well, I don't want to say the main reason, but one of the reasons that it's very low is because of their planting configurations that they're having, that they do in Beaumont. Here in Weslaco, we use it's called a pineapple configuration, which is basically using more efficient use of the water and also the land that we have. And then the sweet sorghum, we use 10. Literature said that you can go up to 14, but we wanted to be this is the result from that study in Willacy County, so that's why we just kept it at 10 dry short ton. Production cost, and this is average for plant cane and for ratoon. For those of you that don't know, for energy cane, same thing as sugar cane, you plant 1 time and you harvest 5 times. So this cost is basically an average of plant cane and then for ratoon. About the same in all the areas, little bit different here in fertilizer, pesticide applied. In Beaumont they have more issues with, I think it was the rice borer in that area. Water, Beaumont they didn't use that much. They have a lot of more rainfall than we have. 2 years in a row here and also in Weslaco we're in a drought, so we use 2.5 acre feet for Weslaco, 2.9 for Corpus Christi. For the seed cost, we use basically what the sugar mill charges, and they use what they say they wanted to use the one that is close to Louisiana, because they work a lot with the Louisiana people, and they use that cost as a seed cost. Then you have your variable cost, your fixed cost, rent. We use these from the crop budgets that we have from different areas for District 9, District 10, and District 12. Well, this too is irrigated. Here you got a little bit of irrigation as well. Here's our return for growers. We use again 20%. So it's 20% above an average cost of about $700. And the expected standing feed cost is 43, 41, and 55, and 47 for sorghum. When you look at sweet sorghum, it's a lot cheaper, but at the same time your yields are lower. And your growing season is a lot smaller as well. Excuse me. We got our fixed harvest and harvest and hold, and then we got our variable. The way that the sugar mill charges is on a per acre basis and then on a per ton per acre. So just to get, they control the harvesting. So they send all the harvesting equipment. You have to send the harvesting equipment on a per acre basis. They charge $92, and then they charge about $10 per dry ton that they harvest on that specific site. That will give us our expected delivered feedstock to the plant of about 58, 56, and 72. Rule of thumb, if you get it for less than 60, it has a high chance of success. And we're right there. What makes it 72? Difference between 20 and 19 to 14. So the key is to maintain 1920 over there, which of course keeping your cost of production in control as well. I mean, under control. You know, don't try to spend too much on fertilizer, because there's 2 things happen when you spend a lot of fertilizer. Your costs go a lot higher, and also your life cycle analysis result goes a lot higher as well. Your footprint basically is a lot higher. We use, again, you know, we're economists. One monk and myself, we don't have I guess an engineer, chemical engineer to do this conversion. So all the conversion technology parameters, which are well known around the industry, we use it from NREL, and it's a national revenue something. It's a federal group. We got the data from enzymatic. Our model has the capabilities of having 4 different conversion processes. Here we're presenting 3. The last one, which is the ABE conversion, that's the one that BP is interested on, which is acetone, butanol, and ethanol that is converted. We're still working on that. That's the last one we added to our model. We didn't want to present it because we haven't tested it yet. But here we're going to present results on enzymatic hydrolysis, fast pyrolysis, and gasification with FT synthesis. Our annual plant capacity, we have it in gallons and million BTU. The reason that we have both is that depending on the technology that you use, you can have either ethanol or gasoline or diesel. And those three have different BTUs. Ethanol usually 70% of gasoline. So if we want to compare apples to apples, we put it in million BTUs, the amount of energy that you're going to have. But for simplicity, also put it in gallons because that's the way the industry thinks as well, and that's the way I think as well. Or we economists, when we look at different studies, it's on a per gallon basis. Average biofuel yield from feedstock, we get a fixed capital investment sources. We get equity that generates dividend and a loan that is specified a specified interest rate. So basically, we will calculate 60% is going to be a loan that you're going to get through a financial institution, and 40% is going to be raised within the company. And if you raise that money, you also have to pay dividends. So everything is included: the interest that you have to pay for the loan, and also the dividend you have to pay for the money that you've raised. And we got a stochastic biofuel and byproduct prices as well. Again, this comes from the EAI. Parameters for a conversion plant here, we have all three: hydrolysis, pyrolysis, gasification. The end product for these three will be either ethanol, diesel. Byproducts, you get electricity in hydrolysis and gasification. You have nothing on pyrolysis. The plants, again, these parameters come from the literature. In order to be commercial scale, basically, they say it will be 61 for hydrolysis, 76 for pyrolysis, and 42. This is a million gallons per year. The yield, 80, 65, and 61. That's per dry ton. The conversion of dry ton, you get 80 gallons. So in the terms of hydrolysis, 80 gallons per dry ton of this material. We used to have 70, 75 at Chevron. The chemical engineer there said that 80 is pretty much what they're getting right now. So that's why we left it over there. But we've run some sensitivity analysis of those numbers as well. Operating expenses, dollars per gallon, you got 50 cents, 70 cents, and then 30 cents. You got your fixed expense. And then you got your total capital investment, your TCI, which is, this is your total. And here you see that's the reason why gasification doesn't make much sense right now, because your capital expenses are too high. Just putting the plant and all the capital expenses are a lot higher than the other ones, and your conversion yield is not very good as well. You got your conventional plant, steam plant, and your land. How much you're going to charge? Again, this is pretty much coming from the literature. 60% is going to be under a loan. We use an 8%. When we gave this presentation to Chevron, they said you can go as low as 6%. Again, we ran some sensitivity analysis on this one, and this is going to give a big, it's going to change. It's very sensible. The results are very sensible to how much you're charging on your interest rate as well as your discount rate for your net present value. Yes, a little bit on the pro-forma. We simulated pro-forma for 10 years. Planning horizon is 10 years. We have our income statement, cash flow, and we got some more information on what goes into it. But it's basically a pro-forma statement. You got your income statement, you got your cash flows, and you got your balance sheet. And once you have your balance sheet, you can calculate your annual net worth and the present value of your ending worth, as well as this one that we use a lot, which is the net present value. For those of you that remember your finance classes, if your net present value is positive, it's a good investment. If it's negative, it's not a good investment. Because again, we're using stochastic yields and stochastic prices, we're using probabilities. So it's the probability of economic success is basically 95 chance of positive net present value. A little bit of the price incentives that we have, and we calculated without any price incentive and with price incentive, just to see how much they impact our bottom line. Byproduct first, we sell the excess electricity to the grid. There's a second generation biofuel producer tax credit, which is $1.01 per gallon if it qualifies as advanced biofuel. The advanced biofuel basically is if you the requirement for it to qualify as an advanced biofuel is that it reduces your life cycle analysis or your carbon footprint by about 60% compared to fossil fuel. Then it qualifies as an advanced. Then you got your renewable identification numbers. that basically tells when was it produced and from what source is produced this biofuel. So an ethanol is not just ethanol. It's ethanol produced from advanced biofuel or from corn. They have different price support and they have different connotations, you know, for depending on the RFS, which is a new renewable fuel standard. So yes, ethanol per se is not the same, even though it's the same product. Depending on where it comes from, it's different, and that's why the U.S. was sending ethanol to Brazil and bringing ethanol from Brazil. The difference, we're sending corn ethanol and we're bringing sugarcane ethanol. Same product, just the one from Brazil, it fits into our renewable fuel standard thing because we have a requirement for every year. And that's what it makes it work right now, because if you have D5, which is the advanced biofuel, with sugarcane it's part of it, you get an additional 69 cents per gallon for this. And the way that we calculate it basically is a cost reduction. So because you're producing this product, on top of the market price, you get an additional 69 cents or reduction in your cost, either way. So you got $1.01, and then you got your 69 cents. Those are the two main price supports for this advanced biofuel. If it's corn-based, you don't get any of these two. There's a ring. If it's corn-based ethanol, you don't get this one, and you don't get that one. For corn-based, I think it's about 30 cents. And the reason that it increased a little bit is because of the shortage in corn production that we had last year, that we were actually importing corn. So anyways, I just wanted to show here the ethanol, the price forecast. Again, you know, depending on the forecast, it's, you know, all our analysis on a 10-year planning horizon. So we just lean on the agencies that do that. They as a living, that's what they do. So we just said we're going to use their forecast instead of us trying to forecast. But there's 3 different forecasts that they have. And for ethanol, you got the reference price, you got the high price, and you got the low price. For ethanol, it doesn't change that much. But for diesel, for example, this is your reference, this is your high, this is your low, depending, of course, of petroleum prices. So we also did some sensitivity on what happens if it's high, the base, and the low as well. And here are the results. These are the expected cash cost overview. And again, this is using 70% of your feedstock from energy cane, 30% from sweet sorghum. Eventually, we're going to have energy sorghum and Napier grasses as well as part of the portfolio, and then we will do we're developing a linear programming model that is going to tell us what combination is the best one. I'm going to talk a little bit about it at the end. These are the 3 different conversion processes: hydrolysis, pyrolysis, gasification. Again, hydrolysis is ethanol, pyrolysis and gasification goes into diesel. That's the production. These are their costs. This is the total cost. For hydrolysis, you got $2.30 per gallon. For pyrolysis, $2.65. For gasification, $3.04. That's just without any incentive. Once you start getting the incentive or the sale of the byproduct, electricity, this one there's nothing because there was no byproduct for pyrolysis. But this one, you sell electricity, your costs go a little bit down. Then you get your RIN. So it goes down by 69 cents. So you go from 238 to 159. And then if you add the $1.01, it goes to 58 cents cost of production because of all that incentive. Here's the problem with those incentives. They have to be approved, or at least the $1.01 has to be approved every year by Congress. So you don't want to build, you don't want to invest $500 million in a plant, depending on if government is going to pass or not. We already saw what happened with biodiesel. They got rid of it, and then after a year, they put it back, but they, mess up the industry because, you still have to pay your notes. And if you think that you can produce at 58 cents, and then they increase it by $1.01, it's going to be a problem for you to make it. Then we have the different components of your cost. For hydrolysis, it's 70 cents 77 cents is your feedstock cost. That's what it costs you. Then you got another 70 cents is going to be your operating and fixed. Then you got your investment, and then you got your dividends. So that's your cost structure. Okay? As you can see, feedstock is very important. That's what I mentioned to you. If we keep it below 60, that's what it makes it work. And in order to keep it below 60, is keeping your yields at 19 and 20. We got a question from the meeting that we had a couple of weeks ago. If it's profitable, how come there's no more of it? Well, you know, we have the 19 and 20 we haven't seen in a constant basis. We haven't seen those type of yields, and we're just starting. We're using 1 year right now. We got data from last year, but this year we got 19 and 20. This one's a little bit of life cycle analysis. I don't want to go too much into it, because these are results from the grid model. And basically we divided here what's the carbon footprint in terms of gram per dry short ton of plant cane and ratoon cane. So you got your farming and harvesting. This is the footprint. You got your fertilizer use. You got your pesticide use, and you get your transportation. That's again in terms of grams per dry short ton produced. The difference here with ratoon cane, and this is using, we don't have the budgets for ratoon cane for our project. This is using the extension budget that I have in the valley. And in that extension budget, basically for ratoon cane, you need to use double the amount of fertilizer. That's why you see that huge increase in the fertilizer, in the footprint of ratoon cane due to the increase in fertilizer. If you can reduce your amount of fertilizer, that's going to make a huge impact on your life cycle analysis for this energy cane or any feedstock that you're using. It's very, very, very sensitive to the use of fertilizer. These are energy use and emission from E85. That's basically the flex fuel card. Then you got your fossil fuels. That's going to be this is the vehicle is going to give that much. The ethanol man and the ratoon cane. This is the contribution or energy use for each of these categories. If you can see on greenhouse gases, the vehicle is going to produce, but the cane is going to have a reduction. You see what I'm saying? Basically what it's showing you is that on the emissions part, the use of energy cane is going to reduce your greenhouse gases compared to fossil fuels. Yes?
What's the second one? Sorry, I know you want to be.
Coal?
Coal?
Yes. And the reason that it's negative is because we use about 20 to 25% of coal for to produce energy in this country. The reason that it's negative for coal is because when you produce ethanol or biofuel, you're replacing some of that coal that you will use for this production with the electricity that you generate by burning, that co-generates using this feedstock. Remember with sugarcane, when you produce ethanol, you use the bagasse and you burn it to create energy. So basically the mills are energy independent. Well, something like that happens as well. You get all the lignin and you produce it into biofuel, and everything else you burn. So basically you're reducing your use of coal. So you're displacing your use of coal. Okay? This one is a relationship on the fertilizer emission, okay, grams per dry metric ton to the percentage of total emission. Look how important is the use of, you also grams of nitrogen fertilizer per metric ton, and this is your gram of CO2. So basically how important is the use of your fertilizer on your total footprint, on your total emission of greenhouse gases. It's really, really, really high. That's why when we see this value here, when you double the use of fertilizer, your footprint just goes really high. And then the last one on life cycle, and this is again for hydrolysis. Each conversion process has its own different numbers, but again, we just wanted to show you what besides doing the economic analysis, we're also doing the environmental, because they have to go side by side. If you don't qualify for advanced biofuel, you're going to lose about $1.01. Okay, so, and not only that, but because of the RFS, they require X amount of advanced or biomass biofuel. Then if you produce just regular biofuel, you're already over the cap that they have of 15 billion gallons. So anyways, this is the total energy product, and this is the three different bars are, one is for E10, so it's ethanol, consumption of 10% ethanol, vehicles to consume, that only have 10% ethanol, E85, which is 85% ethanol, 15% gasoline, and then you got your ETOH, which is 100% ethanol. When you look at here, you see the total energy consumption to produce this ethanol. When you get, go ahead.
The brown is 15% ethanol.
No, 15% gasoline. Yeah, E85, that means ethanol 85, or 85% ethanol. E10 will be 10% ethanol, and ETH will be 100%, basically the cars that you have in Brazil. The reason that you have in total energy, more energy consumption basically, is because for fossil fuel, the energy is already produced, it's stored. But for ethanol, you have to produce it. You have to burn energy to produce this biofuel. But all those biofuels are offset because it's renewable. So basically, you remember coal? We talk about coal. You basically displace this amount of coal by producing, by generating your own energy, producing this biofuel. When you look at this last one, and again, you know that the important here, the one that RFS is interested is in this one here. And this is basically a reduction of greenhouse gases compared to fossil fuel. E10 will reduce 6%. E85 will reduce 75%. 100% ethanol will reduce 98%. Remember what was the number to qualify as an advanced biofuel? 60. So this method, using this conversion process, using this feedstock, will qualify as an advanced biofuel. And you get all the benefits, and you're going to be in that category with the RIN, etc., etc. Okay, there's a lot that goes into the production, and there's a lot of background into it, but basically the bottom line, and this is what I wanted to show you, is this is what the Chevron is interested in. Is this material going to make us qualify for that amount? Because right now, we're just paying for ethanol, we're paying to import ethanol from Brazil, with all the shipping costs and everything. And basically that's what we're going to do with natural gases, and see how do they stack as you know, compared to fossil fuel. 60 is the magic number. These are the net present value for the three technologies. This is without any incentive. Okay? These are CDF, cumulative distribution function. You got millions of dollars here in the x-axis. You got probability from 0 to 1 on this one. Let's start with the black one, for example, which is hydrolysis. Here what it tells me, it has about a 5% chance of negative net present value. So by definition, this one has economic success because it only has 5% chance of negative present value. The red one has about, what, 55, do you think? More or less has a 55% chance. This one is pyrolysis. And then the last one is gasifications have no chance of being economically viable. Why? Capital expenses were very high. Conversion from the yield, basically, the conversion yield was very low, 61 compared to 80 with hydrolysis. Hydrolysis with those, with 19 to 20 dry short tons per acre makes it very close, or if it's 95, it makes it basically, by our definition of economic success, it's a good one. These are the, just using hydrolysis because it's the one that has higher chance of profitability. This is using Weslaco, Corpus, and Beaumont yields. As you can see, Corpus, because they got a little bit higher yields than in Weslaco, it has higher chance, maybe just a 2 or 3% chance of negative net present value. Weslaco, what we talk about 4 or 5%, and then we got Beaumont because low yields for 14 tons, you get about 20. And that's what right now, the question is 20 high enough for people, for investors not to invest? And it looks like it is, because we haven't seen any commercial scale biomass production. Again, if you're going to invest $500 million and have that all risk, you want this to be as low as possible. These are some sensitivity analysis that we have run, and basically the box that is on green has a 95% or higher chance of negative 95 chance of positive net return. Yellow is between 0 and 94, and then red means there's 0% chance of positive net present value. Okay, so let's just run through Weslaco. Using no credits. Remember that I use different prices for oil? You got high oil prices, reference, and low oil prices. What is interesting here is that with high oil prices, for hydrolysis in Weslaco actually reduces your chances going, instead of reference. Because remember that our product here is ethanol. Ethanol didn't have that much of a change. But if you go for hydrolysis is ethanol, this is pyrolysis. Pyrolysis is diesel, so it's ethanol, diesel, diesel. That's my end product. For Weslaco pyrolysis, a reference diesel prices give you 47% chance of positive net present value. With high oil prices, you get a 97%. Very sensitive to the projection of your energy prices over the next 10 years. Do we take the reference or do we take the low oil prices? This is without credits, this is with credits. What happened with credits? Almost everything works. The problem is that you're going to depend on the government to approve or not approve those payments. You have to be here. If you're an investor, you want to see this, no credit. Can we compete in the market? Giving our cost and giving our price that we're going to be selling our product. Again, going to hydrolysis for Corpus Christi, using, again, their yield. At the reference price, you already got a 98% chance of positive net present value. That one goes along with this. This gives me basically this. There's a 2% chance of negative net present value here. If we can, big if we can maintain 19 to 20 dry short tons per acre, this will work the way that it is right now, using reference prices. If we can maintain. Okay, that's a big if. But we showed that at least, for this year, we will be able to make it if we get 19 and 20. Now we have to sustain it. We have to maintain it. And we only have data from plant cake. How much reduction in production or yield is going to happen with ratoon cane? We don't know yet. Remember that this is assuming an average for 5 years. Can we maintain an average of 19 for 5 years? I don't know. We don't know yet. Next year, we'll find out about our first ratoon, and we'll let you know if I get invited again. But anyways, it's if we maintain it. That's, again, it's a big if. That's what makes it work. This one is sensitivity analysis on the discount rate. You use discount rate to bring it to the present value, the net present value of all your future cash inflows. It's very, very sensitive to the discount rate. We use 6%, but if you increase your discount rate to 8%, it's really, really bad. If you reduce it to 5%, makes it a lot better. We're using this one here. Oh no, we're using this one here, sorry. And then we have sensitivity not only we have sensitivity on your discount rate, we have sensitivity on your dry tons per acre, going from 15, 17 to 20. So let's use 6%. And we get 17 dry short tons per acre. And we only get about 70 conversion. This is gallons per dry short ton. We're at 81. If we can make it better to 80, basically they can be more efficient in converting this feedstock into the biofuel, then we jump from 81 to 96. Now, if we can produce the 20 that we're producing right now, at 80 is almost 100% chance. So those two things have to happen. Either you get more efficient at converting the feedstock that we're providing into biofuel, or you get higher yields. Or both. I mean, ideally you get both. If both of them goes higher, then you get more green. So anyways, this is using energy cane and sweet sorghum. This last one, and basically here you got returns to producers. Remember that I mentioned that we use 20%? Here 0%, that means we're not paying the producers for this. It's just basically their cost of production, which is not very realistic. 20%, that's what we use. What about if it's 40%? If it's 40%, if we have to basically pay the producer 40% above their cost to produce this stuff, then it takes us down to 87%. Don't you as a producer, you have to say, okay, is it that enough or is not? Is it 20 good? Well, 20 is good for the plant, but 40 is better for the producer. But of course, it increases your cost. And it makes it, again, lower your probability of success. This is your standing feedstock cost. This is your transportation cost. And this is your delivery cost. As long as you stay under 60, then you're okay. If it's a little higher than that, rule of thumb, again, this industry we use a lot of rule of thumb, 60 is the magic number. For yields, 19 and 20, with a cost of production of about $700 average for plant cane and ratoon cane. A couple of things that we're working. One is we're working on a multi-criteria mathematical programming. It's a LP program that we're going to use a different combination of feedstock. Right now we have data of energy cane, sweet sorghum, and we're working on a grant that we got an internal grant to work on forage sorghum. We also got another grant with Jamie to work on Napier grasses. We're going to have 5 different crops that we can use. And we're going to use our LP model is going to say, okay, what combination of these 3 crops, given the area that you're growing it, what combination is the best? What combination will give you your lowest cost or your higher probability of success, but at the same time minimizing your greenhouse gas emission, because you don't want to go below 60%. So let's say in Weslaco, the combination might be 60% energy cane, 20% Napier grasses, and 20% sweet sorghum. In Corpus could be 60%, 30, and 10. And Beaumont might be a little bit less. We're going to have sites in San Angelo. We're going to have sites in College Station. We already have sites in Beaumont, Corpus Christi, and Weslaco. We have one in Pecos. And we're working with folks in Temple on an IFA grant that we got, so they can do the modeling to fill in the blanks and not given the data that we will supply to them to fill in the blanks and do their production function for these crops in other areas of Texas, and eventually to expand them. So anyways, like I mentioned, energy in mist cane, we're going to use sweet and forest sorghum and Napier grasses, and it's going to let basically the model pick us what the best combination given the area that you have. So I'm very excited about that one. And then the last one is the computable general equilibrium model that it's the PhD colleague that we hired with the Chevron model. With the Chevron project, that was part of his dissertation. And basically, you're going to talk about land use change, economic impact. When you include in-plant as well, you're going to have what's the economic impact of putting a plant in X area, and how everything else is going to change. Your crop mix, your agricultural production is going to be impacted by putting it there. The energy companies will be interested because that'll be how much jobs they're going to generate and any externalities that is going to have associated with putting a plant in that specific area. So We have already the data on each single county in agricultural production, value of agricultural production, percentage of agricultural in each county here in Texas, about 254, and we're working on a paper on land use change, and we're going to incorporate that into whatever we have on biofuel. So I think it's going to be very interesting. And then the WIN model, which was developed by the Policy Center, Dr. Henry Bryan, he's put is a global model addressing trade and policy issues associated with biofuels and greenhouse gases as well. So we're going to be very busy this couple of years, but I mean the amount of information that we're going to generate is going to be amazing, and good information. I think we're going to be able to answer a lot of questions, relevant questions that the industry is asking right now, and see basically if it's going to make sense or not, economic sense. Any questions?